Previous session, we saw gradient descent. So sometime what we have a function and we want to maximize or minimize this function, right? So we will use several optimization method and either we can maximize that function or minimize that function, right? So first method is very simple. Here we will use first order derivative, right? So we will calculate gradient, we will calculate derivative, we will set that gradient or derivative to 0, and then we will solve this equation to get the optimal value of parameters, to get the minima or maxima value, right? The other method is the iterative method, right? Gradient descent. So here if we want to minimize something, if we want to minimize any function, then we will use gradient descent. If we want to maximize something, then we will use gradient ascent. So gradient ascent is for maximization and descent is for minimization, right? And for minimization, we will always move in the opposite direction of gradient, right? So as you can see here, it's a iterative approach, right? So we will here do random initialization. We will start unknown parameter W randomly, and then we will apply several iterations, right? And each iteration, we will compute gradient. So suppose here, 80th iteration, gradient is GT. Then using this gradient, we will apply this equation iteratively, right? And since here we are always moving in the opposite direction of gradient, so therefore here we are using negative sign, right? If we are doing maximization problem, if we are solving maximization problem, then here we will use positive sign. So positive signs means we are moving in the direction of gradient. Negative means we are moving in the opposite direction of gradient, right? Then we also discussed several examples, right? So let's say if we want to reach, let's say this position, right? So here we have the minima value or the function is attaining minimum value for this particular value of unknown. So here, how can we reach if we always move in the opposite direction of gradient, right? So here the direction of gradient is negative. So we should move in the positive direction. This side the direction is negative, so opposite of negative is positive, so therefore we will move in the positive direction to reach at this location, right? Okay, so if we are minimizing something, then we will move in the opposite direction of gradient, right? Now here in this equation we are having two terms, right? This is the old value of unknown. W2 plus 1 is the new value of unknown. So new value is equal to old value minus learning rate time the gradient, right? Okay. So now this gradient can be a scalar or can be a vector. So if we are minimizing or maximizing a function that is having only one variable, then in that case this gradient will be a scalar. But let's say if we are minimizing or maximizing a function that is having let's say n variable, in this case this gt will be a n dimensional vector, right? So this gradient can be a scalar, can be a vector, depending upon what type of function we are minimizing or maximizing, right? If function is a univariable function where function depends on one variable, in that case, gradient will be a scalar, else gradient will be a vector, right? Okay. So if we want to do this type of update here, we need to calculate, we need to have two values, gt and eta t. So eta t is the learning rate and this gt is the gradient here, right? So if this eta t gt is a big number, then this change in w will be large, right? If this eta t gt is a smaller number, then this change in unknown value w will be small, right? So this eta t zeta t can be a small value, can be a large value, right? So if your learning rate is very high, learning rate is very high means this eta t is high, then this eta t gt will be large, and in that case this update will be more, right? So you can see here, since if we are using very large learning rate, then it may start oscillating, right? Why oscillating? Because in this case, this eta t gt is a large number, right? So if we add here a large number, right? So we will move from this position to this position, right? On the other hand, if this learning rate eta t is very small, then this eta t gt, this product will be small, and we will move to this position very slowly, right? So therefore, it will take too long time for the convergence, right? So we need to tune these two parameters, eta t, gt, right? Okay. So gt we can calculate, right? So gt is a gradient, so that we can easily calculate. Here we need to tune or we need to find eta t, right? So eta t is a hyperparameter, and we need to find the correct value of hyperparameter. And there exist several methods to decide how can we find the optimal value, the correct value of eta t, right? Okay, and depending upon our problem, what type of function we are minimizing, we can choose any method to optimize or to get the best value of eta t, right? So eta t is a hyperparameter, and one method is to we can use cross validation. We can use cross validation to decide the correct value of eta t, right? Okay. Yes, and the other parameter is the number of iterations, right? So here we don't know how many iterations we have to apply using this equation to reach at the optima positions, right? So iterations we have to calculate, and the learning rate we don't know, right? So we can tune eta t and the number of iterations using so what we can do, we can use different value of iterations, and then we can calculate whether our algorithm has converged or not, right? So we discussed in previous session, we discussed three types of criteria to check whether our algorithm has converged or not, right? So if algorithm has converged, then in that case the new value will be nearly equal to the old value, right? So Wt plus 1 nearly equal to Wt if our algorithm has converged, right? So let's say if we have already reached to this position, now if you calculate the gradient vector, or if you calculate the derivative, right? If let's say at this minima position, then gradient will be 0, right? Or let's say if you are let's say if you are within this local region, then the gradient will be very small, right? Close to 0. So if you have reached let's say at this position, then at the time the gradient vector or the gradient will be 0 or nearly 0, right? So if this gt is 0 or nearly 0, then this product will be 0 or nearly 0. So in that case, Wt plus 1 is nearly equal to Wt. So that's why we can use this condition to check whether our algorithm has converged or not, right? So if algorithm has converged, then at the time Wt plus 1 will be nearly equal to Wt, or the gradient vector will be nearly equal to 0, right?
I have a question.
Yes.
Is there a way to deduce the starting value of this, or is it completely random?
Initialization part.
Yes, for t.
Yes, so t is equal to 0. So yes, so t is equal to 0. We will start from W0, and W0 we are doing we are starting from random initialization, right?
What about eta?
No. So eta is the learning rate at the tth iteration. So eta can also be changed for with respect to the number of iterations. So for example, at the 0th iteration or the first or second iteration, we are using some value of eta learning rate, and then let's say after 10th iterations, we may change this value too, right? So this eta t is not fixed throughout the training of our model. Yeah, it may be same. It may be same if we are using same value of eta t for for all iterations, then we are using a constant or fixed value for eta t, right? But eta t we can also vary as our model gets trained, right? So what we can do generally, what people do, initially they will choose a high value for eta t, and then as we move ahead, as we train our model, after a few iterations, we will decrease eta t, right? So then what we can do, we can have several types of scheduler, and it's a job of scheduler to decrease eta t, right?
So starting value we can choose as random, and typically which is high, and later on we can reduce this.
Yes, yes, and this is one method, right? The other method is we can have the a constant or fixed value throughout the training of our model, right? And in fact, what some and in fact there also exists several other methods. There we what we can do, we can sometime increase this learning rate, sometimes we decrease this learning rate, right? So it is also possible, right? So what I mean by sometimes we also use scheduler, right? So in sine function, what we have, since we have this, I think you already know the
Correct.
shape of sine function, right? So
Yeah.
if we are using, if we are following sine function, then sometimes it will increase the learning rate, sometimes it will decrease the learning rate, right? So there can be several types of scheduler, right? So here, what scheduler will do? Scheduler will change learning rate with respect to the iteration, right? And yes,
Okay.
and also for the initialization, we do have several methods, right? So for example, JVR initialization is there, right? Or random initialization is there. So here I'm only discussing the one very simple method of initialization, which is nothing but the random initialization, right? So we will initialize these values randomly, but it is not only the method. In fact, there also exist several other methods, just like this, for example, JVR initialization, right?
Okay.
Any other doubt?
Now,
Okay. Yes. So here we need to calculate this gradient, right? Then only we can move in the opposite direction of gradient, right? Now, depending upon how we are calculating this gradient, the gradient descent algorithm can be categorized into these three types: batch gradient descent, stochastic gradient descent, and mini batch gradient descent, right? Which means if we are calculating this gradient using all training data, then that method is called the batch gradient descent, right? Okay. So how are we calculating this gradient? We have one function, and we are differentiating that function with respect to unknown parameters, right? Okay. So let's say if we are solving a regression problem, in case of regression problem, what will be the our function here? So let's say if we are using MSE function, MSE error, then this will be our function, right? Mean square error. If we are using mean square error, then this mean square error is our function, and our job here is to minimize this MSE function. So we have to calculate the optimal value of theta, because theta here is, we are taking as unknown, right? So we need to calculate the optimal value of theta such that this MSE error is as low as possible, right? So here we are minimizing MSE error, right? So we need to find the optimal value of theta, right? And for the optimal value of theta, MSE error will be minimum, right? So here we will differentiate this loss function MSE with respect to theta, right? So when you differentiate this MSE with respect to theta, we will get the gradient vector, right? We will get this GT, right? So as you can see here in this formula, MSE formula, we are having all training data, right? Because we are having m number of data points. We are having m number of data points. So as you can see here, we are calculating this loss for all training points, and then we are doing this summation and then we are doing this averaging, right? So because it's a mean square error, right? So first we are calculating errors, then we are doing squared operation, then we are doing summation, and then we are doing this averaging, right? Okay. So since here we are calculating this error using all training data, and if we differentiate this function with respect to unknown parameter theta, then we will get one gradient vector. And if we use such gradient vector, then that method is called the batch gradient descent, right? Because in batch we will compute this gradient uh, using all training data, right? Okay. Now, what we can do, we can also calculate error for 1 point at a time, right? So, for example, for ith training data, if we can calculate squared error, right? So, for example, let's say we are having one training data, let's say ith training data, we can calculate theta transpose that particular value xi to get the model prediction for ith training data, and the corresponding the ground truth or corresponding output is yi. So we can calculate this difference for the ith training data, right? Because this inner term theta transpose xi minus yi whole square is nothing but the error, squared error for ith training data. So if you consider error using ith training data, and if you calculate gradient only using ith training data error, then that method is called the stochastic gradient descent, right? And in mini batch gradient descent, here we will compute this error using a subset of training data, right? So we can calculate error, we can calculate MAC error for a single training data, we can calculate MAC error for complete training data, we can calculate MAC error for a subset of training data, right? So so that's why we have here three types of method, right?
What is the use of calculating it for a single value?
So yes, I will discuss that point.
Okay.
Yes. So we can have three types of three variants of gradient descent: batch, stochastic, and mini batch, right? So if we are calculating GT using complete data, then batch gradient descent. If we are calculating GT only using a single data point, then stochastic gradient descent. And for mini batch gradient descent, we will compute this zeta t using a subset of training data, right? Okay, so let me ask one question. If you are computing the zeta t using all training data points, then this gradient computation step will be faster or slower?
So
Slower, because we need to calculate first the total error, the complete error using all training examples. So we need to first calculate this quantity, then only we can calculate the differentiation part, right? So if you use batch gradient descent, then the gradient computation step will be heavy, right? The gradient computation step will take a longer time, right? Okay. But since you are computing gradient using all training example, the gradient will be the accurate gradient, right? Because we are calculating gradient using all training example, which means the now the gradient will be the accurate, right? So we will get an accurate gradient, right? Okay. So gradient descent is an iterative approach. We have to apply several iterations, and in each iterations we will use this equation, right? Now, if my gradient is accurate, then within few iteration I will reach at the um, minima position, right? So let's say, as you can see here, since we have only function of one variable, and each time we are using accurate gradient, so within very few iterations we are able to reach at this position, right? But let's say if my gradient is noisy, if my gradient is not accurate, then it will take a more number of steps to reach at this position, right? Okay. Okay, so in case of batch gradient descent, since I am calculating gradient vector using all training example, so my gradient will be accurate, and within few iteration I will reach at the uh, minima position, right? Okay, so if we are using batch gradient descent, then in that case gradient will be accurate, and number of iterations will be less. Within very few iterations, we will reach at the minima position, right? But now the problem is this gradient GT computation step will take longer time, right? Because we need to first calculate error using all training data, and then only we can get the gradient vector, right? So this grade GT calculation of GT will take longer time, right? But the number of iterations will be less, right? So this is the benefit of batch gradient descent. Now let's discuss stochastic gradient descent. In stochastic gradient descent, we are calculating this gradient by only using one example at a time, one training example at a time, right? So if we are calculating GT by just using one training example, which means we only have to calculate theta t xi minus yi whole square. So we are only calculating this inner term, right? And once we have this inner term is nothing but the error for the ith example, right? So if we are using this error for ith example and we are calculating GT, right? So the calculation of GT will be now much faster, right? So we can very quickly we can calculate this GT value, right? Because now we are only calculating GT using single training example, right? But then the problem is the number of iteration will be huge, right? Because if you calculate GT by only using single example, the GT now is not the accurate one. GT will be approximated, right? Because we will have now there exists randomness in the calculation of GT, because we are only relying single training example, single training point we are relying to calculate GT, right? So in this case, GT will be the approximate one, and GT will not be accurate. And if gradient is not accurate, it will take more number of steps to reach at this position, right? Minima position. Okay. So which means if we are doing stochastic gradient descent, then this GT calculation of GT will be easy, right? Very quickly we will get this gradient GT value, but then the number of iterations will be huge, right? And mini batch is you can imagine is um, is a is a combination of batch and the stochastic one, right? So because in stochastic, what is the problem? In stochastic gradient descent, the problem is we are getting a noisy gradient, right? We are getting the noisy gradient, and in batch gradient descent we are getting the accurate gradient, but then the calculation the calculation of GT will take the longer time, right? In stochastic gradient descent, very quickly you can calculate GT, but then the problem is the GT is noisy, right? So we will use the mini batch gradient descent, where we will compute GT by using a subset of training example, right? So for example, let's say we are having thousands of training data point, and we are calculating this GT by only using 10 examples at a time, right? So we will choose 10 examples and we will calculate GT. So now if you are calculating GT using 10 examples, so gradient will be more accurate as compared to the case where we are calculating GT by just using the single example, right? Okay. If you calculate GT by using all thousand examples, then GT will be correct. GT will be accurate, right? If you calculate GT by just using single example, GT will be noisy. if you compute GT using let's say 10 examples at a time, then GT will be more accurate as compared to the case where we are using only one example, and will be less accurate than the where we are calculating GT using the complete training example, right? So mini batch gradient descent, you can think we are using to overcome problems in batch gradient descent and stochastic gradient descent, right? Okay. Yes. So this slide I have already covered, right? So what let's say if we have several unknowns, then we need to first calculate the partial derivative. We need to calculate the gradient vector, right? So how can we calculate gradient vector? If we are having several unknowns, we will calculate we will differentiate that function with respect to one unknown at a time, and while keeping all other unknown fixed, right? Yeah. So suppose we are having a function of let's say three unknown, theta1, theta2, theta3, and if you calculate the derivative will here is called the partial derivative, which is nothing but the partial differentiation of this function with respect to unknown theta1, comma, partial differentiation of this function with respect to unknown uh, theta2, partial differentiation of this function with respect to unknown theta3, right? So you will get a vector here, right? So this vector is called the gradient vector, right? And we will use this gradient vector uh, uh, to update model parameter, right? Yeah.
Hi, I have one question, basic
Mhm,
question.
mhm.
So for gradient descent, actually, we are measuring the gradient,
Mhm.
and also like why we are trying to get optimal values, because so that gradient doesn't toggle outside of global maxima or minima, right?
Sorry, can you repeat your question?
Yeah, yeah. So I
Mm.
am just trying to understand. So this is purpose of gradient descent is to fit so that we get MSE minimum, right?
Yes, yes.
That is the final purpose. So optimal values, local maxima or
Mhm,
minima we are trying to get, right?
mhm.
First. So
Yes,
is
yes.
that the purpose is that so that gradient doesn't toggle outside of that range, right?
Mhm. So here, what we want to get the optimal value of unknown vector or unknown parameters, right? So let's say if we are solving a minimization problem, we want this W, right? Because if we use let's say this W star, for that W star, this function will be minimum, right? And for that, we will always move in the opposite direction of gradient, right? So we have to first calculate gradient, then only we can move in the opposite direction, right? Now, if you are only relying a single data point, because this loss, how can we calculate this loss function LW? Let's say here, if you use, let's say here we are having some W value, some W value. If you put that W value, you will get the some value here, right? So if we are having n, and let's say loss function, we are, and this loss function can be any function, right? But assume this loss function is a MAC function. So for any for any given theta, if you want to calculate what will be the loss for that theta, we need to put here all data points, right? So let's say if there are m number of data points, we have to calculate error using all training data points. Then only we can get the total MAC using that particular theta, right? So if we are calculating gradient using complete data, then that gradient will be the accurate gradient, right? But let's say if you are only relying on one single example to get the gradient vector, then the gradient vector will not be the actual one, right? Because we are approximating gradient, we are calculating gradient by just using single example, right? But we should calculate gradient by using this equation. But we are not calculating using these equations. We are only relying one single training example to calculate the gradient. So that's why that gradient will not be the accurate one, right? Because the accurate gradient is the one that I'm showing in this figure, right? Because this gradient I'm calculating by using all training example, right? So if gradient is not accurate, then it will take more number of iterations to reach this position, right?
Are you taking some example to make us little more understandable? How to put the value, how to from where we'll get all these value which we need to be put in the MSC and then in another equation.
Yes, yes. So I will cover one example right later. Okay, so but here I'm showing one example, right? So suppose this is the function using gradient, we can very easily optimize the unknown parameter w, right? Okay. Okay, so let's say if we have some unknown values, unknown parameter theta, then in first step, what we will do, we will randomly initialize our unknown values, right? We will randomly initialize theta, and then we will calculate this GT gradient, right? Okay. Now, since here we are having several unknowns, so this GT will be a vector, right? Because we have to partially differentiate GT with respect to unknowns, right? So we will get a vector. So GT will be a vector, right? Okay. So let's say if we are having some function, so we will partially differentiate that function with respect to theta1, then we will partially differentiate that function with respect to theta2, right? So that way we can calculate the partial differentiation. Okay. Now we will use that zeta t, and we will apply this equations, right? New value is equal to old value minus learning rate time gradient, right? Okay. So if you use yeah, if you use this MAC loss, if you use this MAC loss, and if you perform differentiation with respect to unknown theta, then you will get this value, right? Yes. Okay, so in theta we are having several unknowns, right? Because theta is a vector. Theta is a vector where we are having several unknowns. Theta 0, theta 1, theta 2 up to theta 8, right? So we are having several unknowns. So we will differentiate this function with respect to theta j, right? So because we need to differentiate this function, MSE function, with respect to theta 0, then theta 1, then theta 2, right? So we will calculate here partial derivatives, right? So if you differentiate that MSE function, you will get this function, right? Okay, so how can we perform that partial differentiation? Let's say if we have yes, so let's take this function, MSE function. So the differentiation of x square is, let's say if we have function y is equal to x square, if you differentiate this function with respect to, let's say, dy by dx, what we will get 2x, right? So here if you differentiate this because here theta is a vector, right? So we will have here theta 0, theta 1, theta 2, and so on, right? So we will differentiate this function with respect to theta 0, theta 1, theta 2, right? Partial differentiate this function. So if you partially differentiate this function, MSE function, let's say with respect to any particular theta, let's say theta j, then we will use this y is equal to, if we are differentiating y is equal to x square, then after differentiating we will get 2 times x, right? Okay, so the same here we can apply here. So it will be the 2m, right? Then summation I is equal to 1 to m, right? So 2x, right? So it will be 2 we have already written, so it will be theta transpose xi minus yi, and then we have to differentiate this part, right? So if you differentiate with respect to theta j, so in theta we will have several theta values, theta 0, theta 1, theta j, right? And the corresponding x value, right? So x1, x2, x3. So since we are differentiating theta with respect to theta j, and we are keeping all other theta constant, so here we will get the term xj, right? So if you differentiate this function with respect to theta j, you will get this value, right? So as you can see here, we are calculating partial derivatives here, right? Okay. So if you differentiate MSE with respect to theta, we will get this gradient, and we will use this gradient to update the to update this equation, right? W nu is equal to W old minus eta t times dt, right? Okay. So this is the gradient. This is the partial derivative with respect to theta j, right? Because in theta we are having several unknown value. In theta we are having theta 0, theta 1, theta 2, and so on, right? So with respect to theta j, we are partially differentiating while keeping all other theta fixed, right? Okay. So this way we can calculate, we will get the vector, right?
Can you please go back to previous screen? The
This
last
slide.
on the last element you have got xji. What does this represent?
No. So see, here we are having several theta values, right? So if we are having linear models, then what will be our model here? theta 0 plus theta 1 time feature 1 value, right? X1 plus theta 2 x2 plus theta 3 x3 and so on, right? So this xj is the corresponding xi to this theta j, right? So for example, here for theta 2, what term we will have here? X2, right? Because we are partially differentiating it with respect to theta j while keeping all other theta constant, right? So if you are differentiating, if you are partially differentiating with respect to theta 2, which means all other thetas are constant. So since all other values are constant, so if you differentiate with respect to constant, what value we will get? 0. So here also what value we will get? 0. So only here we will get the x2, right? For corresponding theta 2. So for theta j, we will get here xj, right?
Yes, thanks.
Okay. Yes. So if we are having, let's say, three thetas, theta 0, theta 1, theta 2, then we need to compute gradient vector, right? So let's say if you are differentiating function, MSE function is let's say function f theta, f of theta. So we need to compute del f by del theta 0, del f by del theta 1, partial differentiating this function with respect to theta 2, right? So we need to compute this vector if we are having three theta values, right? So this is how we are calculating one partial differentiation. Let's say del by del theta 1, right? So we need to compute del by del theta 0, del f by del theta 2 also, right? Okay. Yes. So if you compute the gradient with respect to all unknown thetas, we will get this vector, right? Here, what this first term represent? Partial differentiation of MSE error with respect to theta 0, right? Because theta 0 is the first unknown, theta 1 is the second unknown, right? And we have n such unknowns, right? So we need to calculate, we need to estimate these n unknowns, right? So this gradient will be a vector of size n plus 1, right? Because there are n plus 1 unknown, right? Okay. Yes. So here I've shown calculations for one theta j, right? And if you arrange all, if you calculate all such partial derivatives, you will get the gradient vector, right? Okay. So if you put all these values here in this vector form, and if you do some arranging, then finally you will get this type of equations: 2 divided by m xt x theta minus y, where what is this x matrix? X matrix is the matrix that we will get after arranging data points row wise, right? So remember this capital X matrix I have already discussed, right? In this X matrix, what we will have here, we will have data points row wise, right? Okay. So in capital X matrix, we will have data point. So let's say first row is the first data point, second row is the second data point, third row is the third data point, and so on, right? So this is our X matrix, right? Now, as you can see here, in this gradient computations, we have taken all data points, right? Which means if you use this type of gradient in updating a known value, then that method is called the batch gradient descent, because we are calculating gradient using all training examples, right? Any doubt here? Okay.
How did this 2 by m that equation came?
No. So let's say if
X.
you are differentiating some function of form x square, then differentiation will be 2 times x, right?
Okay.
Yes. So here also we are having square term, right? In mean square error, MAC error, we are having this square term. Okay, let me show you this term.
Yeah, that's
So
there. Yes.
yes, so due to this square, we are getting 2 times the inner part, right? 2 times x. Yes. And this slide I have already discussed, right? Because in gradient calculations, we are taking complete data point. We are using all data points to compute this gradient vector, which means the batch gradient descent is terribly slow on the large training set. If we are having thousand or if we are having millions of data points, then this calculation, this gradient calculation will take very long time, right? Yes. So since batch gradient descent uses entire training data to calculate gradient, so that's why this batch gradient descent is terribly slow when we are having large data sets, when we are having millions of data points in our data set. Then this batch gradient descent method will be very slow, right? Yes. So if we are having yes, and we already discussed this solution, normal equations, right? We can use normal equation to solve linear regression problem, right? So there we discussed that if we are having uh, thousands of feature, then we cannot use we cannot use. So in normal equations, we have to invert a matrix. We have to invert a matrix of size, feature cross feature, right? So if there are thousands of feature, then we have to invert a matrix of size 1000 cross 1000, right? So in normal equations, linearly. Uh, so normal equation we will use uh, if we are having less number of features, right? Yes. So this step I have already discussed, right? It's nothing but the same equations here that I've shown. New value is equal to old value minus learning rate time gradient, right? So new value is equal to old value minus learning rate time this gradient, right? Here I'm using GT to show the gradient vector, and here we are writing this function to show this is the gradient with respect to gradient of MAC with respect to unknown parameter theta, right? Okay. Yeah. Yes, and since we are minimizing this function, so we will always move in the opposite direction. We will always move in the opposite direction of gradient, right? Okay, now let's discuss the implementation part of batch gradient descent, right? So here we will use these equations, right? New value is equal to old value minus learning rate times the gradient vector, right? Okay, so assume here the eta value is the 0.1, right? This learning rate value is 0.1, right? And the number of iteration is 1000, which means we are iterating these equations 1000 times, right? So here the number of iteration is 1000 and this eta t value is 0.1, right? Yes. Okay. So here we will first initialize, we will randomly initialize theta value, right? So theta is equal to np.random.rn, this function 2 cross 1. So it will randomly initialize theta values, right? Because here we are having two values of theta, theta 0, theta 1, right? So we are learning a linear regression model, right? Linear regression model. The model here will be the y is equal to theta 0 plus theta 1 times x, right? So we are having two theta values, theta 0, theta 1, right? So we are randomly initializing, and then we are iterating using this equations, right? New value is equal to old value minus learning rate time gradient. Yes. So gradient we already know, right? So for gradient we will use this equations, right? So this is our gradient for complete data points. So here we are using this value as a gradient, right? Okay. And then we will use these equations to update, right? Theta new is equal to theta old minus learning rate time gradient, right? And gradient we are calculating using this equation, right? So since here in this case we are having two theta values, theta 0 and theta 1, so we need to calculate del by del theta 0 and del by del theta 1, right? Okay. So we need to first set learning rate. Then we need to decide number of iterations, how many times we want to iterate that equation, right? Okay. M here is the number of data points, number of element in training data set. So here we are having 100 data points, right? This theta is nothing but the unknown vector that we are estimating, right? And here, since we are having two theta unknown value, theta 0, theta 1, so we are randomly initializing two values, theta 0, theta 1, right? So that's why here we are having size 2 cross 1, right? Because we are having two theta values, theta 0, theta 1. So we have to initialize two values randomly, one value for theta 0, one value for theta 1, right? And then we will use several rounds of iterations, right? So we will calculate gradient, vector, and we will use this equations to update the theta values. New theta is equal to old theta minus learning rate time gradient, right? Okay. So if you apply this iterations 1,000 times after iterating, you will get the optimal value of unknown parameters theta. So this 4.21509 is nothing but the optimal value of theta 0, and the second value is the optimal value of theta 1, right? And the similar value we will get if we use the normal equation method, right? Yes. So here we are having 1,000 data points, and we are applying 1,000 iterations using this equation, right? And after iterating, the final values of unknown theta we are getting here 2.41 for the theta 0 value and 4.30 for the theta 1 unknown, right? Any doubt in this code? Okay. Okay, now let's discuss how the learning rate affect the gradient descent, right? So this part also I have already covered, right? I have shown this visualization. If you choose very small value for learning rate, it will take a longer time to reach this position, right? If learning rate is very high, it will start oscillating, right? So these examples I have already covered, right? Yes. So here, if you choose a very high value for learning rate, and if you start a gradient descent algorithm, as you can see, we are moving, we are oscillating, right? If you decrease this learning rate, then this loss very easily we can minimize, and we are able to reach the optima position, right? But if you increase this learning rate, it will start oscillating, right? As you can see here, right? It will start oscillating around the optima position, right? If you are taking sorry, if you are choosing a very yes, okay. If you are taking, let's say, this is the random initialization, right? We have to randomly initialize weight and biases. So assume randomly you are initializing from -4 value, and bias is the 10 value, right? And the learning rate is very small. And now if you apply this gradient descent, as you can see here, it will take several rounds of iterations to reach this optima position, right? Because this theta values, the unknown values are moving very slowly, right? Now, if you see this visualization, if you increase this learning rate, the change in value will increase, right? If you increase, let's say, let's say this is my learning rate, 3 into 3.1 10 to the power of 5. Now you can see here this line is changing, right? And if you, yes, so this is the perfect learning rate, right? 0.002. If you use 0.002, then yes, within very few iterations you are able to reach the optima position, right? Here the learning rate is 0.002. Yes, I'm starting. Yes, within very few iterations you are able to reach the optima position, right? But if you are choosing very high value of learning rate, now you are oscillating around the optima position, right? Okay.
Can you please explain why is it oscillating?
Because if you take eta t is a, let's say eta t is very high value, then eta t gt will be a very high value. This number will be very high, eta t zeta t, right? So if this value is very high, which means one time you are having positive gradient, other time you are having negative gradient, right? So let's say this side you started from this side. Now here the gradient is negative, right? And since you are taking a very high value for learning rate, eta t, then this eta t gt will be a large value, right? And since this eta t gt is large value, which means the change in w will be large, right? And if change in w will be large, which means you will move from this position to this position. Now again, if you calculate gradient direction of gradient has changed. This side we will have negative gradient, and this side now we are having positive gradient, which means again the shift or the jump will be you will make a big jump, right? So which means now you will start oscillating around this position, right? Because one side you are having positive gradient, other side you are having negative gradient. So positive, negative, positive, negative. So that's why you will start oscillating around this position, right?
Okay. So is it possible to detect that it is oscillating and then put a stop?
Yes, we can calculate the direction in gradient. If direction is gradient, let's say if we are having positive, then negative, then positive, then negative, which means we are oscillating around that position, right?
Yeah. So in that case, we can, if let's say that situation occurs, then we can.
So we can decrease the learning rate, right? Because I showed one visualization, right, where if we decrease the learning rate, the oscillation will stop, and we will reach to the optima position, right? Okay. So this visualization I have already covered, right? If you take very small value for learning rate, it will take several iterations to reach the optima position, right? If you take very big value for learning rate, it will start oscillating, right? Yes, so this slide I have already covered, right? So learning rate, we cannot take a very small value because then it will take a huge number of iterations to reach the solution, right? If learning rate is too low, it will take lots of time to reach the solution. If learning rate is too high, it will take it will start oscillating, right? So we will jump here and there around the optima position, right? So learning rate has to be not too low and not too high, right? If you choose this learning, if you choose the correct value of learning rate, then within very few iterations you will reach the solution position. You will get the optimal solutions, right? Now the question is, how can we find that this is the good learning rate, right? Okay, so one method is what we can do. We can do the grid search, right? So we will have several. We can try several value of learning rate, and we can select the suitable learning rate, right? But here the problem is we need to, since it is an iterative approach, so we have to use several iterations to get the solution, right? Yes. So we can use grid search to find the good learning rate, right? But then we limit the number of iterations, right? Because we are here having two unknown, right? Yes. So this W is again unknown. W is unknown. And we also don't know the number of iterations and the learning rate, optimal value, the correct value of learning rate. So this eta t, correct value of eta t, we don't know. The number of iterations we don't know, right? And W is also unknown, right? So this eta t and this iteration, number of iterations is called the hyperparameters, right? And W is called the model parameters. So in gradient descent, we are having two types of parameter. One category of parameter is called the model parameters. Model parameters are the unknown parameters that we are estimating here, right? So here unknown parameter are this W vector or this theta is the unknown parameter. Eta t and number of iteration is eta t is also a parameter. Number of iteration is also a parameter, but this type of parameters we call hyperparameters, right? Because the performance of this algorithm, the performance of this gradient descent depends on number of iterations and learning rate, right? So this learning rate, iteration, these parameters are called the hyperparameter, right? Yes. So we can use grid search to calculate the learning rate. Yes. And how can we choose and yes, we can also use uh, the cross validation. So what we can do, we can try several value of learning rates, and we will pick learning rate that maximizes our accuracy or that minimizes our error, right? Yes. Okay, so how can we set the number of iterations, right? So this I've already discussed, right? There are three ways to decide the number of iterations, right? If this GT becomes small, or let's say if the solution doesn't change anymore, right? WT plus 1 is nearly equal to WT, or let's say if whenever we are getting the error below some certain threshold, at that point also we can stop, right? Because let's say for this position, optimal position, the value of this loss function will be small, right? So if let's say if this LW value is the value for this optima position, the loss value for this optima position is below some threshold, then that condition also we can take as a stopping condition, right? Okay. Yes. And also, if the number of iteration is too low, then we may not get the optima solution, right? So let's say if let's say learning rate is small and the number of iteration is also small, then let's say we may stop at this. We may not reach to the optima position, right? Yes. And if number of iteration is too high, then it may also possible. Let's say if you are taking very small learning rate and the number of iteration is also very high, then it will take more number of iterations, more number of update. It will take huge time to get this position, optima position, right? Okay.
So there
it
are
will.
two
Yes.
minimas here, right?
Mhm.
One is global minima and the other is the local minimum.
Yes.
So
Yes.
by gradient descent, we can be stuck at any of these two. How will we
Yes.
know
Yes.
that we are at the global minima?
No, we cannot calculate this, right? So the gradient descent algorithm will give any one. So let's say if you are for this function, if you are using gradient descent will give you either this solution or this solution, and it depends on what type of initialization we are using, right? And what type of learning rate we are using, and how many iterations, we are doing, right? So depending upon our learning rate, depending upon number of iteration and our initialization, we may get either this solution or this solution, right? Okay, but for this linear regression part, we will not. So linear regression, we will not have any problem, because this function that we are minimizing is a convex function, right? X square is a convex function. X square is a parabola, right? So in this type of function, we will only have one solution, and that solution is a global solution, right? So here, if you use gradient descent for convex function, you will always get the global solution, because in this case we will only have one solution, right? So for MAC loss, we will not have any problem, right? But this method, gradient descent method, we can use for any loss function LW. This loss function can be MAC error, can be absolute error, or can be any function here we can take for LW, right? So if LW is the MAC function, then since MAC is a convex function, so we will always get the global solution, right? Any other doubt? Okay. Yes. So here the common practice is we will set a large number of iterations, and we will stop our algorithm when the gradient becomes tiny, when gradient becomes uh, nearly equal to 0, right? Or 0. So what we can do, we can, let's say, we can set number of iteration to, let's say, 1,000, right? And let's say after 100 iterations, if gradient becomes teeny, then we will stop at that point, right? Because we don't know how many iterations, how many times we have to use this equation to get the optimal value, right? Number of iterations we don't know. So what we can do here, we can choose, let's say, 1,000 iteration, and let's say after 100 iteration, if this GT becomes teeny, then we can stop after 100 iteration, right? If WT plus 1 is equal to WT, or let's say if GT is 0, or let's say the error function, let's say, is below some threshold value, we will stop that point, right? Okay. Now, how can we calculate the gradient becomes too teeny? For that, we can use any norm, right? So, for example, here, let's say if you have a vector x1 to xn, the norm you can calculate using this formula, right? So, if norm of this vector is below some predefined threshold epsilon, we can stop that at that point, right? Right? Because here in gradient descent, uh, if function is having several unknowns, then we will have this vector, right? Gradient is a vector. Right. So since here we are having vector, so we can calculate norm of that vector, right? So if norm of that vector or the magnitude of that vector is less than epsilon, we will stop it. Right? Okay, so for MAC, for mean square error, the batch gradient descent with a fixed learning rate has a convergence rate of order of 1 by iterations, right? So if we divide this epsilon by 110, the algorithm will have to run about 10 more times iterations, right? So let's say if new eta, new threshold is is nothing but the old eta divided by 10, right? If you divide eta by 10, right? Now let's say if the new threshold eta is the previous value of eta divided by 10, right? So this algorithm has to run 10 times more iterations, right? Because here we are having divided by 10, right? Okay. So any doubt in batch batch gradient descent? Batch gradient descent is very simple. The only difference in batch gradient descent is we will compute zeta t using all training examples, right? Okay. This stochastic, we will compute zeta t by using one example at a time, right? So batch gradient descent problem here is this algorithm is slow because we need to compute gradient using all training examples. So what we can do, we can use stochastic gradient descent. So stochastic gradient descent, just pick one random example from training set and compute gradient by just using that single example, right? Yes. So now this SGD makes algorithm much faster because in each iteration, very quickly we can compute this gradient, right? Because in GT we are only computing using one example at a time. So GT computation will be easy, right? But here the problem is, since we are computing gradient by just using one example, so that gradient will be noisy, right? Because now this gradient is not the actual gradient. This gradient we are calculating using one single example. So we will follow here the zigzag path, right? Because this gradient is not the actual gradient, right? Okay. So let's say if we have 10 data points, so let's say one data points, using one data point, this is the direction of gradient, right? Let's say G1. This is the direction of gradient G2 when using second data points, let's say G3, G4, and so on. Let's say G5, right? So assume we are having 5 data points, so we will have 5 gradient values. G1 is the gradient value using one first training example. G2 is the gradient value using the second example. So if you compute the gradient using all training example, then this G will be the average vector, right? So here G will be nothing but the G1, G2 up to G5 divided by 5, right? So in batch gradient descent, this gradient vector will be the average gradient vector, which will be the accurate gradient, right? But now since we are not using G, we are only relying either G1, G2, or G3, right? So therefore, this gradient is not the actual gradient, but right. So therefore here, if we want to reach to this optima position, it will follow this zigzag path, right? Because this gradient is noisy here, right? So cost function bounces up and down and decreases on average because here we are following a zigzag path, right? Yes, and if you see this optima region, here also we are moving. We are bouncing, right? Because we are using the noisy gradient, right? So once we are in the optima region, in optima region also we will continue to bounce around, right? Because here the gradient we are using is the noisy gradient, right? So it will never settle down, right? Okay, so how can we fix this problem here? Even if we have reached to the closer to the optima position, we will not get the solution and we will continue to bounce around, right? So now how can we fix this problem? This problem we are getting because we are using noisy gradient, right? We are calculating gradient using single example, so that's why we are facing this problem, right? So how can we fix this problem? So we will start oscillating around this position. So what is the solution? We will decrease the learning rate, right? So how can we fix this problem? We will simply decrease the learning rate. Once we are close to the optima position, we will decrease our learning rate to to stop this bounce around the optima position, right? So it will settle down our algorithm, right? Okay. Okay, so we will get our solution, but since we have not settled down, so therefore that solution will not be the optimal. So to get the optimal value, we will decrease the learning rate, right? Yes, this slide I have already discussed, right? So depending upon our initialization, our learning rate, number of iterations, either we will get the local solution or the global solution, right? Yes. So this technique also I have covered, right? Stimulate annealing. So what exactly we will do here? We will start with the high value of learning rate, and then we will decrease the learning rate as we train our model, right? Yes. So this part also I have already discussed, right? We cannot take a very high value for learning rate. We cannot take the very small value of learning rate, right? Yes. So then what we will do, we will use the learning schedule. Learning schedule means how we can decide that what will be the learning rate for the TF iterations, right? So for that, either we can use the fixed value for all iterations. So let's say eta t is fixed. Eta t is 0.01 or 0.001 throughout the training of our model, right? Or we can start with the high value, then we can decrease, right? Or we can use any other scheduler, for example, sinusoidal scheduler we can use, or any other type of scheduler we can use. So what this learning scheduler will do, learning scheduler will change learning rate for any particular iterations, right? So this eta t is the learning rate for the T8 iterations, and learning rate scheduler will give us this eta t value, right? Okay, so now let's implement stochastic gradient descent. So in stochastic gradient descent, we will calculate gradient using one uh, one one data point at a time, right? Okay, so let's take a 5-minute break and then we will see code for stochastic gradient descent, right? Okay, so let's start. Hello, am I audible?
Yes.
Okay. Yes. So here in stochastic gradient descent, we will compute gradient using one example, right? So assume we are having, let's say, three data points we are having. So what we will do, we will randomly pick one data point. We will randomly pick one data point. So suppose this point we are choosing first time, right? Now using this data point, we will compute gradient and we will apply, we will, yes, we will apply this equation, right? Okay. So, and let's say next time, we are choosing this data point as a randomly. So we will compute gradient and then we will update model parameters, right? And let's say next time we are choosing this second data point randomly, and we are updating parameters, right? So this way we can choose one data point at a time randomly, and let's say in data set, let's say we are having three data points, and if we have update our equations over all training data points, so that is called one epoch, right? So epoch means we have completed one round of updations, right? Which means we have updated equations, we have updated models using all training examples, right? Yes. So here by convention we will iterate rounds of m iterations. Why m iterations? Because we are having m data points. We are having m data points, and in stochastic gradient descent, we will compute gradient using one data point at a time, right? So therefore, we will use here m number of iterations, right? Because in each iterations we are calculating GT using single training example, right? So since we are computing GT using one training example at a time, so therefore the total number of and since we are having m number of data points, so therefore there will be uh, m GTs, right? Yes. So let's say here you will get some gradient if you use this data points. If you use this data point here, again you will get some gradient. So let's say the G1 gradient, G2 gradient, G3 gradient, and you will use these gradients to update the model parameters, right? So each round is called the epoch. So epoch means when you have completed all data points, uh, right? So let's say if you have 10 data points in your data set, and epoch is let's say epoch is 5 epoch you are using, then number of total number of iterations will be 10 into 5, 50, right? Which means 50 time you will update using this equation, right? Okay. Yes. So in gradient descent, so yes, so this is our learning scheduler, right? So learning scheduler is taking t as an input and returning this value as an output. T0 divided by t plus t1. where T0 and T1 values are 5 and 50, right? Number of epoch, we are choosing here 50. So epoch means one complete round of updation, right? Which means we have seen the training data once, right? So let's say if number of epoch is 50, which means 50 times we will go through the complete data sets, right? So which means each data points we will use 50 times, right? So first data points we will use 50 times, second data points we will use 50 times, right? So in each round we will select data points randomly, and once by doing these random selections, if we have covered all training examples, that will count as a one round, one epoch, right? Any doubt here? Okay. So here this number of epoch we are taking 50, T0, T1 values are 5 and 50. If you put here any T value, it will give it will give you some value, right? And that value we are taking as a learning rate lambda. That value we are taking as a learning rate eta t, right? So to get eta t for any iteration t, we are using here the scheduler, right? Okay. Now you can also verify here, as you increase t value, T0 divided by T plus T1 will decrease, right? Because let's say this T0 is fixed. T0 is fixed 5. So 5 divided by T plus 50, right? Because T1 value here is 50. So 5 divided by T plus 50. So if you increase uh, this T value, the learning rate value will decrease, right? Yes, because here you are returning T0 divided by T plus T1, right? So T0 is 5 divided by T plus T1 value is 50, right? So if you increase T value, 5 divided by T plus 50 will decrease, right? Which means for high value of T, this quantity 5 divided by T plus 50 will be smaller. That's exactly what we want, right? If the number of iteration is large, then learning rate has to be the small. So this scheduler we can take, right? So this is one example of scheduler. But this is not you can define any scheduler, right? Scheduler means for different value of t, we will get the different value of learning rate, right? Okay. Yes. Okay, so here we are randomly initializing because we are having two unknown, theta 0, theta 1. So two values we are initializing randomly, right? Okay, then we will here apply several rounds of iterations, right? So how many rounds we want here? 50 rounds. So for that we are writing here for epoch and range number of epochs, right? So 50 round we want. And in each round, in each epoch, what we will do, we will randomly select one data point at a time, right? So how many data points we are having here? M, small m is the number of data points, So suppose if we are having 100 data points in our data set, then small m will be 100, right? So we will take here, as you can see, we are taking here this value randomly, right? So xi, xi is the ith input, yi is the corresponding output. So this xi, yi, which means the point we are taking here, we are selecting using random procedure, right? Randomly we are selecting one point at a time, right? Okay. So here, what exactly we are doing? We are calculating a random index, right? We are calculating here the random index, and using that random index, we are fetching that training data point xi, yi, right? So since here we are using random functions, so every time we will get a new data point, random data point, right? Okay, so randomly we are selecting one data point, and using that data point, one data point at a time, we are calculating gradient, right? So this gradient calculation we are doing only for the single data points, right? And if we have the gradient, we will use that equations, right? Theta is equal to theta new value is equal to old theta minus learning rate time gradient, right? So this eta is nothing but the learning rate. And this learning rate, how we are getting this learning rate? We are getting this learning rate using this scheduler, right? So this scheduler is giving us this this learning rate eta, right? Okay. So any doubt in this code? Since here we are calculating gradient by only using one example at a time, so that's why this procedure, this algorithm is called the stochastic gradient descent, right? Okay.
So what is the value of M where we're defining in the range?
No, M is the number of data points. So yes. So M, I think we have already defined. So I think value of M is 100, right? Yes, here we have defined M is equal to 100, which is nothing but the number of data points, number of points in our data set, right? Okay. Okay. So after having 100 rounds, because here we are taking a number of epoch is equal to 50, right? So after doing 50 round, uh, we will get optimal value of, we will get the solution theta 0 and theta 1, right? Yes. Yes. We can also use scikit-learn library function uh, for the SGD algorithm, stochastic gradient algorithm, right? So to perform linear regression using scikit-learn, we will use SGD regressor class, right? And by default, this regressor class will use the MS error, meaning squared error, right? So for that, what we will do, we will import SGD regressor from scikit-learn.lean model, and then we will use SGD regressor function. And in SGD regressor function, we will pass some parameter value. So for example, number of iterations, how many times we want to update this equation. So let's say if you want to update this, apply these iterations 500 times, here you will write 500. If you want 50 iterations, you will write 50, right? Penalty is equal to null. So this penalty I will discuss later, right? So penalty, sometimes we also use regularized. Sometimes we also want L1 regularization, L2 regularization to prevent overfitting. So for that purpose, here we will use penalty. But here we are not using any regularization, so therefore penalty is none. So this penalty I will discuss later, right? So penalty basically we will use to regularize our model to avoid the overfitting, right? Okay. This eta 0 is nothing but the learning rate, right? Okay. So after calling this SGD function, you can pass your data to fit this SGD model, right? So X is nothing but the input data. X is a matrix, right? Where you are arranging data points row wise. Y is the corresponding ground truth. And this RAVEL function we are using here to convert y in a vector, right? Because y has to be one vector, column vector, right? So to convert y to a column vector, we are using this function. So what this RAVEL function will do? It will convert any um, y to a one-dimensional vector, right? Okay. So here you will pass input, you will pass output, and it will fit the SGD. SGD. It will use the SGD algorithm to calculate the optimal value of parameters, right? So suppose if you are having two unknowns theta 0, theta 1, so if you want to print the unknown values, you can use intercept and coefficient, right? So coefficient means theta 1 and intercept means the bias term, right? So y is equal to mx plus c, right? So m is the slope and c is the intercept, right? So if you want to print the unknown values theta 0, theta 1, you can print, right? Okay. So what this AGD regressor will do, it will apply 50 iterations. It will apply 50 iterations using learning rate 0.1, right? So here this eta t is 0.1 and it will apply 50 rounds, 50 iterations, right? And after 50 iteration, you will get this solution, right? Where this first value is the theta 0 value, second value is the theta 1 value, right? Any doubt here? Okay. So now let's discuss mini batch gradient descent. So mini batch gradient descent, as I said, we will compute gradient using a subset of training data points, right? So for example, we are having 1,000 data points, and we are using 10 data points at a time to compute the gradient. If we are using such type of scheme, then that method is called the mini batch gradient descent, right? Yes. So instead of computing the gradient based on the complete training data point or by the just data points, in mini batch gradient descent, we will compute gradient on a small random set of instances called the mini batches, right? So for example, let's say originally we are having 1,000 data points, but we are only taking randomly 10 data points to calculate the gradient. Then that method is called the mini batch gradient descent, and here the size of mini batch is 10 because we are calculating gradient using 10 randomly chosen data points, right? We are randomly choosing 10 data points and then calculating the gradient. So here the mini batch size is 10. Okay. So mini batch gradient descent compute gradient using a small random set of instances called the mini batch. Okay. So this advantage I have already covered, right? So advantage of mini batch over stochastic gradient descent is if you use the mini batch gradient descent, now the gradient you will get the uh, because in case of stochastic gradient descent, we are getting noisy gradient. So it will fix that problem, right? So since now we are getting more correct value of gradient, so the number of iterations required will be reduced, right? So if the number of iterations we are reducing, which means we are getting a performance boost, right? Because if gradient we are getting correct gradient we are getting, then we will get the more correct solution, right? Because if gradient is not correct, then solution will not also be the correct, right? If gradient is you are calculating accurate gradient you are using, then you will get the correct solution, right? So you will get the performance boost. From hardware optimization point also we will get benefit because now we are having we are calculating gradient using uh, gradient uh, uh, using a set of data points, right? So since we are using gradient using set of data points, so therefore we will do here we will perform here the operations using matrices using vectors, right? Yes, yes. So yes, so the if you use the complete data, then this gradient, for this gradient, we will use the X matrix, right? If here you use the, if you use the subset of data points, then what changes we will do here? The only change here is, now in this case, X is not the complete matrix. Okay. In case of batch, mini batch gradient descent, this X will be a subset of original data, right? So let's say originally we are having 1000 data points, and if mini batch size is 10, mini batch size is 10, then there will be only 10 rows, right? Because if mini batch size is 10, we will randomly select 10 data points from 1000 data points, and those randomly chosen 10 data points we will arrange here row wise, right? Okay, so there will be 10 rows in this X, right? And using this formula, we will compute the gradient. So the point that you can note here, now since we are doing operations using matrices, right? Because X is a matrix, Y is a vector. So we are using matrix and this vector, right? So this type of calculations, multiplication, these operations we can perform parallelly, right? So for example, let's say if you multiply two matrices, how we are doing matrix multiplication? We will take here one row, we will take here one column, and then we will do multiply these two to get one value, right? Similarly, for other values, how we will proceed? We will take second row, we will set the second column, and then we will get the another value. So this calculation, the second row, second column calculation, we can do in parallel, right? Parallelly, we can execute. So this type of parallel execution, we can get some benefit if we use GPUs, right? Because in GPUs we are having 1000 core, we are having 1000 core, so parallel computation we can do, right? So this type of multiplications where we are having matrices and vectors, we can do the parallel computation. So it will also benefit if we use the mini batch. So from hardware point of view, we will get the optimum performance, right? Because if you do update one point at a time, then this type of parallelization you cannot do, right? Because we only have one point. But now since you are having 10 data points, so you can do parallel computations, right? Any doubt here? Okay. Yes. Yes. So from hardware point of it is also optimized, right? Because now we are doing metric operations, right? Yes. Mini batch algorithm is more accurate than the SGD, because in SGD we are having noisy gradient, and since in mini batch we are relying on a subset of data points to calculate the gradient. So therefore the gradient will be now more accurate. So therefore this algorithm is less will produce less error as compared to SGD, right? Yes, the disadvantage here is that it is harder for mini batch GD to escape from local minima, right? Because if you are trapped, if you are trapped, let's say at local position, let's say here, if you are trapped, then using SGD you can escape, right? Because in SGD, since gradient are noisy, so therefore since gradients are random, gradients are noisy, so that randomness will help you to move from this local region, right? But since now you are using accurate gradient, gradient randomness, you are reducing from gradient, so therefore uh, uh, it may possible that you trapped at local position, right? But yes, even if you are trapped at the local position, you can skip from these positions using learning rate and the uh, yes, using learning rate. So what you will do, if you are trapped at the local position, you will increase the learning rate so that you can jump from this position to this position, right? So there are lots of hyperparameter and tuning by tuning those parameters, you will get the optimal solution, right? So if you are trapped, then you will increase your learning rate so that you can jump from this position to this position, right? Because if you want to jump from this side to this side, then you have to increase your learning rate, right? Otherwise, for forever you will stuck at this position, right? So it's not like that in mini batch you cannot escape from local minima. Yes, you can escape from local minima if you increase your learning rate, right? Any doubt here? Okay. Okay, so let's discuss the implementation for mini batch GD. Okay, so it's same as the SGD. The only difference is in the gradient calculations we are taking a subset of data points, right? In SGD we are only taking one data point at a time, right? We are only taking one data point at a time randomly. Here we are randomly choose a subset of data points, right? Okay, so same learning function, same learning scheduler here we are using, right? The only difference is here we are taking. So let's say yes, let's say we are having m number of data points. So first we will create m uh, random indices, right? Okay. So this shuffle indices will shuffle uh, uh, and will give you the shuffled indices, right? So for example, let's say if we have 5 data points, 1, 2, 3, 4, 5. So it will do this shuffling operation, and shuffle index will give you, let's say here we are getting first position 5, then let's say 1, 3, 2, and let's say 4, right? And after doing the shuffling operations, we will get the shuffled data points and corresponding output, right? Okay. Now, based on this mini base size, so suppose if mini base size is 2, which means we will compute gradient by using 2 example at a time, right? So originally we are having 5 data points. If you use all 5 data points to compute gradient, then that method is called the batch gradient descent. If you only compute gradient 1 data point at a time, that method is called the stochastic gradient. If you compute gradient using subset of data points, then that method is called the mini batch gradient descent, right? So if here mini batch size is 2, which means every time we will randomly select 2 data points from these 5 data points to compute the gradient, right? Okay. So if mini base size is 2, then we will first take 2 data points randomly, right? So since we have already shuffled these indices, so therefore the randomness is already there, right? Because originally we are having 1, 2, 3, 4, 5, but since we have shuffled this index, so randomness is we have already introduced, right? Okay. So for first time gradient computation, 5 and 2 will go here, right? In this gradient computation, 2 data points will go, 5 and 1. Second time, 3 and 2 will go. And since we are having 5 and we are selecting 2, so this 4 we will skip here, right? So in one round, in one epoch, we will compute 2 gradient, one gradient using 5, 1, second gradient using 3, 2. In another round, again we will shuffle these indices, and let's say after doing shuffling, now let's say shuffle index is 4, 1, 3, 2, and 5, right? So again, mini base size is 2. So first gradient we will calculate using 4, 1. Second gradient you will calculate 3, 2. And since we are only left with the one example, and there has to be two training example to calculate gradient. So therefore, again, we will skip this 5, right? So this way we will proceed, right? Yes, update equation is the same, right? Theta old is equal to theta new minus, theta new is equal to theta old minus learning rate time gradient. The only difference is this gradient we will compute using mini batch number of training example. So if mini batch size is 2, we will compute gradient using 2 training example at a time, right? Okay, so any doubt here? Okay, so after iterating multiple times, we will get optimal value of parameters, right? Theta 0 and theta 1. Okay, so now let's visually discuss all these 3 algorithms in one place. So as I said, in batch gradient descent, gradient we are computing, accurate gradient we are computing, right? So since we are computing accurate gradient, so as you can see in batch gradient descent, the path is smooth, right? From randomly initialized position to the optimal position, we are moving, we are following a smooth path, right? Because here the direction of gradient, because the gradient is accurate, right? In mini batch, or in stochastic gradient descent, since we are computing gradient using one training example at a time, so therefore the randomness in gradient, or there will be error in gradient, right? So that's why this stochastic gradient descent is following a very zigzag path, right? Zigzag path is there because we are having randomness as gradient, right? Gradient are noisy. And in case of mini batch, since gradient is more accurate as compared to mini batch, in mini batch gradient descent, gradient is more accurate as compared to stochastic, but less accurate as compared to batch, right? Because in mini batch we are computing gradient using a subset of data points. So therefore, again, the path is zigzag, but not as zigzag as we are getting in case of stochastic, right? One more observation you can note here, in batch gradient descent, the gradient computation step is heavy, right? It will take huge time to calculate gradient, but the number of iterations required will be less, right? Within very few iterations, you will get your solution, right? Why? Because we are having here the correct gradient, right? In mini batch or stochastic, the number of iterations required will be more, right? Because gradient is not as accurate as the batch gradient descent, right? Yes. So let's discuss these observations one by one. So using all 3 algorithms, we end up getting the same solution, right? Again, this observation is only true for the MAC laws, because in MAC we will always get the unique solution. But if we are optimizing a function where we are having several solutions, local solution, global solution, then we cannot say that every time we will get the same solution. In fact, different run of different same algorithm, you will get the different answer. What I mean, let's say even if you are using batch algorithm, batch gradient descent 3 times, you will get the different solution, right? Because there are multiple solutions, and this algorithm will give you any one solution, right? Okay, but here, since you are optimizing MAC laws, which is a convex function, so you will get the global solution, right? Okay, so that's why all these 3 algorithms end up nearly near the minima, right? So this position you have reached after convergence, right? The second observation is the batch gradient descent path actually stop at the minima, right? So as you can see, you are starting from this position and you are stopping exactly uh, at the minima position, right? But for the stochastic gradient descent, since the gradient is noisy, so therefore even after reaching to the uh, optima position, you continue to bounce around the optima position, right? Because here the gradient is noisy, right? Yes. Yes. So both stochastic gradient descent, mini batch gradient descent continue to walk around, and the reason is since here gradient is noisy, gradient is not as accurate as the batch gradient descent, so that's why even after reaching the optima position, these two will continue to walk around the optima position, right? Yes. Batch gradient descent takes a lot of time in each step. Why it will take lot of time? Because here this computation of gradient is heavy, right? We are computing GT using all training examples, so that's why batch gradient takes a lot of time to take each steps, right? Yes. Yes, both SGT and mini batch GT, we can reach the minimum provided the good learning schedule, right? If learning rate is too high, then you keep start oscillating. Learning rate is too slow, then it will take more number of steps for the convergence, right? So choosing the right value of learning rate is most important when we use gradient descent algorithm, right? Yes, and after training in the final model, uh, we will get the same solution, right? All these three algorithm end up with very similar model, with very similar model, right? Because all these three gradient descent, stochastic, mini batch, and uh, batch gradient descent, finally you are getting the nearly same value of unknown parameters theta 0, theta 1, nearly same value of theta 0, theta 1 we are getting after convergence, right? So since we are getting the same value of nearly same value of unknown theta 0, theta 1, so therefore the same prediction you will get even if you use the batch gradient model trained using batch gradient descent, or if you train model using mini batch gradient descent, or if you train model using stochastic batch gradient descent, similar predictions you will get at the test time, because the value of theta 0 and theta are the similars, right? How can we make the prediction at the test time? Theta transpose x. We will use theta transpose x to get the predictions, right? So if theta values are similar, the predictions will also be similar, right? Yes. So now let's compare the all three gradient descent batch, stochastic, mini batch, and the normal equations, right? So I have already discussed that when we have the large M, when we have the uh, uh, because this normal equations linearly scale with respect to the number of training example, right? Because in normal equations we are inverting a matrix of size number of feature into number of feature, right? So if n is the number of feature here, m is the number of training examples. So in normal equation method, we have to invert matrix of size n cross n, where n is the number of features. So if number of features are large, then normal equation will be slow, because the matrix inversion operation is very costly. So if number of feature is large, then normal equation will be slow, right? And since normal equation method linearly scale with respect to the number of training example, so it will be fast here, right? So if we are dealing with the large number of examples, if we are having millions of data points in our data set, right? So if we are having a huge number of data points in our a large number of data points in our data set, then for that we will use normal equation method, or we can use SGD or mini batch GD, right? But we will not use batch GD, because in batch GD we will compute gradient using all examples, and since the number of examples we are having large number of training examples, so batch GD will be slow, right? Out of core support means can we execute these algorithm without loading all training points in memory, right? So normal equation, it is not possible, because here we are using mathematical equations. So for that we need to load complete data points into memory, then only we can calculate the optimal value of theta. Here also in base GD also we cannot we cannot do, right? Because in base GD we are computing gradient using all training example. So we need to load all training examples in memory to calculate the gradient, right? But in stochastic GD or mini batch GD, we are calculating gradient using a subset of example. So only that particular subset we need in the memory to calculate the gradient. So out of core support is only we will get for SGD and mini batch GD, right? Because in mini SGD, one data point we need to compute gradient. So only that particular point we want in the memory. In mini batch, the mini batch number of data points we want in the memory to calculate the gradient, right? But in normal and batch, the all data points we need in memory to calculate the gradient, or to calculate the optimal value of parameters, right? Okay, large
Mini
n.
batch, for mini batch, this out of core support will depend on the size of the batch, right? Size of the mini
Yes,
batch.
size of mini batch. So let's say if we are having 1,000 data points and mini batch size is 10, then at least we have some memory that we can accommodate 10 data points, right? So let's say 1,000 point we cannot accommodate, 1,000 point we don't have memory. But even if we have memory for 10 data points, we can execute mini batch GD, right? Because mini batch GD only require 10 data points at a time in memory to calculate the gradient, right? So that's why out of core support is present here. Out of core support is present in SGD also, right? Okay, for large n, if number of feature is large, we will not use normal equation, because here we have to invert a matrix of size n by n. So it will make this matrix inversion process very slow. So therefore normal equation we will not use. But yes, if we have the large number of features, then we can use base GD, SGD, mini batch GD, depending upon the number of examples, right? So if let's say if the number of features is large, number of data points is large, then we will not use batch. Either we can use SGD or we will use mini batch GD, right? But let's say n value is large, but m value is, let's say, small, then batch GD we can also use, right? Okay, hyperparameter in mini batch GD and SGD we are having more number of hyperparameter as compared to normal equation and batch GD, right? Because in normal equations we are given, we directly know the equation, mathematical equations, and using that equations we will get the optimal value. So we don't have any hyperparameter in normal equation method, right? Because we are using one equation to directly get the solution. In base GD, SGD, mini batch GD, there are so many hyperparameters, right? For example, this eta t, learning rate is a hyperparameter, number of iteration is a hyperparameter, and in fact in mini batch, the mini batch size is a hyperparameter, right? Because we can take mini batch of 10, we can take mini batch of 20. So what is the ideal mini batch size? So that mini batch again a type of hyperparameter, right? Okay, scaling required. So in normal equation, scaling is not required, right? Because we are here using the mathematical equation. But yes, in batch, stochastic, and mini batch, feature scaling is required, right? Yes. So because if we are not doing feature scaling, then it will follow the zigzag path, right? Yes, I think I have shown one slide. Yes. So if we are doing feature scaling, all features are within the same range, then directly we will follow this path, right? But let's say if features are on the different scale, so for example here for theta 1 features, we are having bigger scale. For theta 2, we are having smaller scale. Then we will follow the zigzag path, right? And since here we are following this zigzag path because features are not on the same scale, it will create problem in optimization, right? So that's why for gradient descent, we need feature scaling. Yes. So base GT, SGT, mini base GT, all these three we need feature scaling. Yes. For
Professor,
normal, yes.
Yes, sorry. I just, so we are already like almost half an hour up. So can we
yes,
continue it next time?
Yes. So this is the last slide.
Okay. Sure. Thanks.
Yes. And the library support for normal equation, we use linear regression package. For stochastic GD, we use SGD regressor package. And for the batch and mini batch, we don't have any support in scikit-learn. But yes, we can code, right? So we can so because in SGD we are using one data point at a time. In batch we are using complete data point. In mini batch we are using subset. So SGD support is there in scikit-learn, but scikit-learn we don't have any support for. So scikit-learn doesn't provide any support for batch GD and mini batch GD, right? But I already shared IPython Jupyter notebook file, so you can use this code to get the optimal value of parameters, right? Mini batch GD and the batch GD you can do, right? Okay, so next session we will see polynomial regression, right? So linear regression we have covered. Polynomial regression we will see in the next session, right? So for linear regression, I have covered 4 methods: normal equation, batch GD, SGD, mini batch GD, but we have several other methods also to solve linear regression. So it's not like that these are the only method to solve linear regression. There are some more methods that we will discuss later, right? Okay.
When is the quiz for this?
I think tomorrow.
So Pravendra, one request. I don't know if everyone will agree, but if we can kind of reschedule it to next week, because today only we have finished this linear regression, right? Is it possible?
Okay.
Yeah,
Would really appreciate.
Yeah,
that will give some time for us to go through mostly the gradient descent part.
Yes.
So next week should be fine, and then we can continue with the same schedule which we already have.
Okay. So I will ask Gajen to reschedule that. You reschedule your quiz, right?
Okay, sure. Thank you very much.
Thank you so much.
thank you.
So up to this, the linear regression will be part of next week quiz now.
Yes, because tomorrow
All
I
the
will
four
cover.
methods.
Yes,
all the 4 methods, right?
Yes, but tomorrow session I will cover polynomial, because in polynomial is nothing new here, right? So in polynomial we will only add polynomial features to get the non-linear relationship, right? So
Okay.
Polynomial regression is very simple, right? Once we know the linear regression, one minor difference is there. We here add the polynomial feature to get the non-linear relationship, right? So
Yeah,
nothing new here.
I think. Yeah, I think in terms of the quiz, whatever has been done till today will be there, or it will also cover polynomial.
Okay, so I will ask Gajendra and let you know tomorrow, right?
Okay, that will be great. Thank you so much.
Okay. Thanks, Professor Pravendra. Appreciate that. Thank you.